All right, let's jump right into this explainer. When you think about shipbuilding, you probably picture the meticulous welding, the insane hydrodynamics calculations, fitting massive engines together piece by piece, right? It's highly precise work. But all of that careful engineering eventually culminates in a single, heart-stopping event, getting the ship into the water. Today, we're looking at one of the absolute most breathtaking ways engineers pull this off. Honestly, it's a process that totally defies our basic instincts for how you're supposed to treat a multi-million-dollar, incredibly complex machine. We're talking about the side launch. I mean, seeing a 10,000-ton vessel just tip sideways off its building blocks into a massive wall of spray. It literally looks like a terrible industrial accident. It is genuinely jarring to watch. The ship is essentially shoved off a ledge. It lands perfectly sideways in the water, rolls incredibly far over, and kicks up a wave that can completely wash over the opposite bank. But it is actually an act of highly controlled chaos. It's a fully engineered spectacle. Naval architects aren't just doing this for the thrill of it. For many traditional shipyards, throwing a ship into the sea like this isn't just an option, it's an absolute necessity. Section 1. The geographic problem. So why on earth would anyone subject a freshly built, freshly painted ship to such a violent drop? Well, it all comes down to geography. When we picture a traditional ship launch, we usually think of an end launch, right? The ship sliding backwards, stern first, down a long ramp into an open harbor. But doing that requires a massive runway of water to absorb the ship's kinetic energy, sometimes up to 300 meters, and that's even with giant drag chains deployed to slow it down. The problem is, a lot of historic and highly productive European shipyards were built on the banks of really narrow inland rivers. These river sites might only offer 100 meters of total width from bank to bank. So it's just basic geometry. Launching a 150-meter ship stern first into a 100-meter river is physically impossible. You would literally ram the ship straight into the opposite bank. So the side launch was born entirely out of geographic necessity. Section 2. Mechanics of the slide. So how do you actually take a skyscraper-sized object and tip it sideways? In a side launch, the entire building slipway is oriented perfectly parallel to the waterway. And this actually gives the shipyard a huge, unique advantage during the years of construction, the total absence of keel declivity. See, in a standard end launch, the ship has to be built on a slant, usually a 1 in 20 slope. So every single worker, crane, and tool is operating on an incline. But for a side launch, the ship is built perfectly flat, level with the ground. It's so much easier. Then, when it's time for the launch, the ship is transferred onto transverse wooden ways. These are basically thick, heavily lubricated wooden tracks running perpendicular under the ship, leading straight to the water. And then the launch itself happens in this fast-paced, heart-pounding sequence. First, the holding mechanisms let go, and gravity immediately tips the massive vessel toward the water. Second, the entire hull slides sideways down those wooden ways. Third, the ship hits the water broadside, smacking the surface with its massive flat side and displacing a colossal volume of water in a split second. And finally, the hull enters this deep, terrifying roll, leaning unbelievably far over before the ship's natural buoyancy finally kicks in and snaps it back upright. Section 3. Surviving the roll. Now, the make-or-break moment of this entire process is that deep roll. Getting the math wrong here means literally sinking the ship before its career even begins. When the hull hits the water broadside, it rolls to staggering angles. We're talking 30 to 40 degrees from vertical. Just imagine that for a second. If you were standing on the deck during a 40-degree roll, you'd be staring straight down at the water, hanging onto the railings for dear life. It looks exactly like a ship that is actively capsizing. But to the engineers on the shore, this extreme angle is fully expected. It's a calculated part of the ship's very first test of transverse stability. To make sure the ship actually survives this roll, naval architects meticulously calculate the launch stability curves way before any steel is even cut. The magic metric here is called the minimum righting arm. Without getting too deep into the reeds of the math, the righting arm is basically the distance between the ship's center of gravity pushing down and its center of buoyancy pushing up. As the ship rolls into the water at that extreme 40-degree angle, this righting arm absolutely must remain a positive number. If it stays positive, the ship's buoyancy acts like a giant invisible spring, forcing the hull right back up. But if the architects miscalculate and that number drops below 0 during the roll, the ship just keeps rolling, goes completely upside down, and capsizes right there in the yard. That's exactly why calculating this stability curve is one of the most critical steps in the entire engineering phase. Section 4. Modern Launch Alternatives. Now, as thrilling as that gravity drop is, the side launch is mostly a legacy of those narrow river yards. The industry never stops evolving, so let's look at modern launching methods. Today, modern yards with broad access to open water, or those with the massive capital to invest in heavy infrastructure, rely on dry building docks and a process called the float-off. It is literally the exact opposite of the side launch. No sliding. No heart-stopping 40-degree roll. Nothing like that. The ship is built inside a massive concrete basin. Think of an empty swimming pool. When the ship is finished, they simply open the valves. Water gently and quietly rises to meet the hull. The ship sits completely motionless on its blocks until the water hits a precise calculated depth, and then it just lifts a centimeter off the blocks. Afloat. If we stack these methods up against each other, you can clearly see why the modern industry shifted. Side launches brilliantly solve extreme space limitations requiring very little waterway width, but they subject the hull to massive dynamic loads and that extreme roll risk we just talked about. End launches, your traditional slipway drop, also apply high dynamic loads and carry their own unique risks, plus they need tons of open water space. But then look at the dry dock float-off, zero dynamic loads. The hull never takes the impact or acceleration forces of gravity, zero roll risk. The space required is strictly confined to the dock itself. It is, without a doubt, the safest, most controlled method available, making it the absolute gold standard for modern yards building today's megaships. Which brings us to a really fascinating final thought to ponder. As maritime engineering continues to scale up, we are building ultra-large crude carriers and container ships that carry 20,000 containers. These vessels are simply getting too heavy, and the structural risks are becoming way too great to just drop them sideways off a slipway. So, are we witnessing the end of the spectacular, controlled chaos of the gravity launch? Will future generations of engineers only ever know the gentle, silent float-off? It's an incredible evolution of industry and physics. I really hope this explainer gave you a totally new appreciation for the staggering engineering it takes just to get a ship wet. Keep learning, and we'll see you in the next explainer.